Dear students, welcome back to the video lectures, and we have reached chapter 4, in which we will deal with stochastic calculus. And in particular, we will discuss sections 4.1 and 4.2 in this video lecture, and there we will introduce a stochastic integration. Yeah, and the aim is to come up with a general definition of a stochastic integral. The general setup here is as follows. We are given a Brownian motion, Wt, t greater or equal to 0, and a filtration, script ft, t greater or equal to 0. And now we would like to make sense of the following stochastic integral. So we would like to define the following stochastic integral. The integral from 0 to capital T of delta t dwt, where capital T here is something like the end time of a financial contract. So we will look at a term delta t dwt over the lifetime of a financial contract. So in fact, we are integrating with respect to Brownian motion here. You see the dwt, which is new. And delta t, the term in front of dwt, that is a stochastic process, t greater or equal to 0, a stochastic process which is adapted to the filtration, script f of t of the Brownian motion. Well, this is new for us, right? We have not yet seen this before, so we need to properly define this. And why looking at such a term? Well, in financial mathematics, such an integral over the time, an integral of delta t dwt, that can be seen as the total gain of a financial portfolio. Now, this is a bit premature because we have not even discussed the portfolio yet, and but we just want to explain you that it actually makes sense to look at this in quite some detail. Yeah. Now, as we did with Riemann integrals and with Lebesgue integrals, for the definition, we start with simple processes. These were the piecewise constants that we have seen before. Before we worked with simple functions, but now we'll work with a whole family, and therefore we will work with simple processes. So let's first define these simple processes. So we will use for delta t simple processes. And the definition is as follows. It's a specially adapted process, delta t, t greater or equal to 0, adapted to the filtration script f of t, t greater or equal to 0 of the Brownian motion on the closed interval from 0 to capital T. It is called simple if there exists a partition of the interval, partition as follows. So 0 is equal to less or equal to t0. It's less than t1, less than t2, up to tn, which represents the end time, capital T, of the interval 0t. So we have a partition, there exists a partition such that the delta t with an event little omega in omega is equal to the sum of I runs from 0 to n minus 1 of delta ti at an event omega times the indicator function which is then 1 between ti and ti plus 1 and 0 elsewhere. So this sum is a simple function. So we are in the following setting. So we have our, this is a straight line, a time interval. And we have, here we have T1, T2, T3, etc. up to Tn, which is equal to capital T. Here is our 0. And then here we have delta Ti, and that is a random based on a random event. So it can be like this, etc. Right? every time our event changes, our piecewise constants will change. That is part of this construction of simple processes. All right, so that is how this is. So delta t is a constant on the interval ti plus 1, and it has the value at the left point of the interval, delta ti. And then it's multiplied by this indicator function, and therefore we get these piecewise constant properties. Yeah. So now let's define the Ito integral. So if delta t greater equal to 0 is a simple process with an underlying partition from 0 to capital T, again, T0 equal to 0 in this case, less than T1, less than T2, up to Tn minus 1 being less than Tn, which is the final time, capital T. Then we define the Ito integral, which is the object of study in this section, as follows. For T, small t in the interval, 0 to T, we look for a K, an index K, such that our T lies in the interval between Tk and Tk plus 1. So we have our timeline again. Our timeline. This is our T0 equal to 0, T1, T2, etc. And then we have somewhere in the end, we have Tn, which is equal to T. And here we have an interval Tk, Tk plus 1. And in this interval, we have our T. And this is the setting that we are in. All right. And then we define the integral. We call it capital I, IT. It's defined as the sum. I runs from 0 to k minus 1 of the simple function delta ti times the Wiener increment. We had the dw in the definition, wti plus 1 minus wti. So these are the first k minus 1 elements. And then the last element runs in this small piece here, in this small piece. And that is delta tk, again, we choose the left side point, times the increment that is remaining, wt minus wtk. Right? So we have the first sum represents the integral up to tk, and the final part here, that is this represented by this small element here. Yes, I would like to stress that this integral, it is a random variable. So that is also the reason why we wrote this omega here. It is a random variable. Yes, so that is an important part. Now, if we take this partition smaller and smaller, so we increase the number of points, and the interval in the partition gets smaller and smaller. This can be seen as Wiener increments. These are increments. And this is the value. So we will be able to define this as the integral from 0 to small t of delta u dwu. So that is the definition of the Ito integral. Again, as mentioned, the Ito integral is a random variable. It's a process, so you have to read it with the omegas here. Yeah, omega, omega, omega. etc. Omega, 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 right? Now let's investigate the properties of this integral IT for the simple adapted processes. So the first thing I notice without doing any work, let me go back to the definition. The first thing I notice is here are increments, Wiener increments. They are multiplied by a constant. This is a sum. These pieces can be small and they are continuous. So the first thing we can notice without too much work is that these are continuous paths. So the Ito integral is made of delta ti. These are constants. It's made out of the increments, and the W has continuous paths. So we see quite clearly that IT has continuous paths. So since Brownian motion has continuous paths, the same holds for IT. All right. Second important property is that IT is in fact a martingale. Remember that in order to have something to be a martingale, we need to show essentially two properties. It should be adapted to the filtration, and we have the conditional expectation property. Well, being adapted is quite clear. If we go back to the definition, here we see that if you look at the time interval, you'll see that we are up to time t, and everything up to time t is related to time point tk. Yeah, and the filtration is an increasing filtration. And all the terms that are appearing here in this first part, all the terms that are appearing here, they are concerned with tk's that are less or equal to t. And the last term here, this last term, that has the t. So every term in this expression is ft measurable. And thus we have adaptiveness, right? So again, let's look at that second property, the theorem that we just mentioned, that the Ito integral IT, where small t runs from 0 to capital T, is in fact a martingale with respect to the filtration script ft, where t runs from 0 to capital T, of the Brownian motion wt, t greater or equal to 0. And we have just seen that the first part of the proof is easy. It's easy to see that IT, from the definition of IT, is ft measurable. And therefore IT, where small t runs from 0 to capital T, is adapted. Each term in the definition of IT is in fact ft measurable. Now the second property is that conditional expectation I just mentioned, and you know the expected value of IT given the filtration up to time s should be equal to is. And this conditional expectation to hold is the second fundamental property of the martingale. For that, of course, we need to look at our timeline, and we have an s less than small t being less or equal to capital T, and small s being greater or equal to 0. Now, in order to investigate this, we look at our timeline. This is again a straight line. And we have our time partition here. Now we look for two indices, an index L, in such a way that our time S lies between TL and TL plus 1, so in this interval, and an index K such that our time point small t lies in the interval between tk and tk plus 1. Yes, so we look for two of these indices so that this is satisfied. S is in TL to TL plus 1, and small t is in TK to TK plus 1. Now let's rewrite the expression having this in mind. So t is then written as a sum. I runs from 0 to L minus 1 first. So we first take the part up to L minus 1 of delta Ti, again, the left point value of the simple process times the Wiener increment. So the increment of Brownian motion, Wti plus 1 minus Wti. And then we reach point L, and there we have delta TL times the Brownian increment WTL plus 1 minus WTL. And then we continue. We go with our index from L plus 1 to K minus 1. Again, we take the left point value for the simple process, delta Ti times the Brownian increment, WTi plus 1 minus WTi, plus the last part, IT is, of course, an integral running to time small t, and small t was in the interval between tk and tk plus 1. So here we have our final term, delta tk times wt minus wtk. All right? So let's look again what this is. So we have the conditional expectation of this expression, in fact. Yeah, under the filtration Fs. Now let's look in detail what we get. So first of all, we have this conditional expectation. So splitting this sum into 4 terms, this is term 1, this is term 2, this is term 3, this is term 4, and these are exactly the sums from the previous page. So this is until L minus 1. This is that specific part between TL plus 1 and TL. This is the part from L plus 1 to K minus 1. And this is the last part. So we have 4 parts. And we look at these 4 parts individually. Yeah. So we can tell what happens with each part. Well, let's look at the first part. Yeah, let's look at the first part. Well, we know that all these points up to TL, all these points are earlier than time point S, right? That is from the definition. So my filtration is an increasing filtration. Every term in the first part here is measurable with respect to FL. And because we have an increasing filtration. So this first part is FL measurable. Again, let's look at the first term. I rewrote it here. I repeated it here. This is Fs measurable. In fact, all these time points are prior to time S. And because they are Fs measurable, we can take out what you know. So the expected value of something which has happened in the past is in fact the value itself, right? So this expectation of the sum I runs from 0 to L minus 1 of delta Ti times this Brownian increment, given the filtration Fs, is in fact the sum I runs from 0 to L minus 1 delta Ti Wti plus 1 minus Wti. And that's it. Yeah, this part is easy. It is Fs measurable. So I can take out what I know, and the conditional expectation is just the value because W is a martingale. Now the second term. Let's look what we have here. In the second term, let's look back one slide. The second term, we have one part here delta TL WTL, which is Fs measurable because TL is earlier than time S. And we have this other part, delta TL WTL plus 1. That requires some extra care. Let's look at them in detail. So we have this expectation to deal with. And as I mentioned, this part, delta TL WTL, that is in fact Fs measurable because TL is less or equal to S. And WTL is Fs measurable. So therefore, take out what you know. We can say this part is also, this part is Fs measurable, take out what you know. So rewriting this conditional expectation boils down to delta TL times the expected value of WTL plus 1 under the filtration Fs minus that other part is Fs measurable. So we can just rewrite this without the expectation minus delta TL WTL. Now we know that W is a martingale, so the expected value of WTL plus 1, the conditional expectation with the filtration Fs is in fact Ws. Yeah, by the definition of W being a martingale. So in the end, that is delta TL times Ws minus the other part, delta TL WTL. So in total, the result from the second part is delta TL Ws minus WTL. And from the first part, this was remaining. Now, if we look again at these two parts, the sum I runs from 0 to L minus 1 of this term plus this term, in fact, if we combine the two, we see that in fact we already have gained, we have obtained what we would like. Yeah. So this is in fact, this is already IS. Yeah. If we would write down IS, the combination of term 1 and term 2 will give us IS, will give us what we want, the conditions for IT being a martingale. So the sum of the answers we got from terms 1 and 2 is already the thing that we would like to have. But we still have these terms 3 and 4 here. Yeah, term 3 and term 4. So the conclusion is that these terms 3 and 4, they should be equal 0, right? They should both be equal 0. Well, let's look again at part 3. In part 3, we have the following. Well, again, let's start with this slide. So the sum of the first and second terms is already equal to IS. And that is the answer that we seek to achieve. So we need to show that the third and fourth terms are both equal to 0. And for that, we use a special technique, double conditional or iterated expectations. So let's see where we are. We are in a setting now that we have, this is my straight timeline again. This is my TL. This is my TL plus 1. Here is my S. And then here we have TK. And here we have TK plus 1. Here we have RT. And we are basically concerned now with this range. And in the fourth term, also with this small range. So these two we need to assess now. And we use that with double conditioning. So the third term, the expected value when I runs from L plus 1 to K minus 1 of delta Ti times WTL ftI plus 1 minus WTI fs. So conditional on fs. Well, the Brownian increment part is independent of fs. Remember this. Remember this from our earlier derivations. The Brownian increment part is independent of fs. And the delta term here, the delta term is FTI measurable, right? So we see that this will go in the good direction, and we will formally do this with a double conditioning. So what I'm going to do is I'm going to condition on the ith term, on WTI. I can do this because Fs is contained in FTI. Yeah. So this is the expectation is linear, so the summation can be taken out. Yeah. So what I do here is the summation can be taken out. So I look in detail at one of these terms. I look in detail at the expected value of delta Ti times this Brownian increment, WTI plus 1 minus Ti, conditional expectation on the information up to time S. So how I do that by this iterated expectations, the double expectation. I take the expectation, an inner expectation, with respect to FTI. So it's the expectation of the expected value of WTI times WTI plus 1 minus WTI, conditioned on FTI, and the outer expectation remains conditional on Fs. Yeah. So this is an example of iterated conditioning, and this technique is used quite often. Now, once I do this, then this term here becomes, well, the delta Ti term becomes FTI measurable, and I can get it out of the inner expectation, right? So I can get it out of the inner expectation. You see it here. Delta Ti is out of the inner expectation. And then I get this term here, which is independent of the filtration FTI. Yes? So this remaining part is independent of FTI. So the conditional expectation is a regular expectation, as we have seen an earlier time, and that is equal to 0. Yeah. So a regular expectation of this Brownian increment is equal to 0. And we can also write it like this. This can be seen as this term minus this term. And in fact, that is equal, this term is WTI. So we remember, this is a martingale, so this is WTI. So delta Ti WTI minus delta Ti WTI is in fact equal to 0. So the third term is equal to 0, which is good. Now let's look at the fourth term. The fourth term is that final part, right? So we were in this setting, straight line again. We are at Tk plus 1. And we look at this, and here is T. We look at this little piece, and F, our time point S is somewhere here. So let's look at this fourth term. And in fact, that goes pretty similarly as before. Yeah, the first part is again this first part is again FTK measurable. And therefore, when I use double conditioning, again, the same as we did for the third term, we can handle this term in a very similar way. So again, FTK is, Fs is contained in FTK, so we can do this double conditioning, and the inner expectation we can look in detail. This is the expected value of delta Tk times the Brownian increment Wt minus Wtk, conditioned on the knowledge at time Tk. And then the outer conditioning is conditional on the knowledge at Fs. Now this part again is ftk measurable, and this part is in fact independent of ftk. So we repeat the same trick as we did before. We take out of the inner expectation delta tk, and we write this down as w, the conditional expectation of wt, conditional on the knowledge up to time tk, minus the measurable thing delta tk wtk. This is a martingale, and then with this knowledge level, this will be equal to wtk. Even netjes schrijven. wtk. And then if we look at it, delta tk wtk minus delta tk wtk is indeed 0. So also our fourth term is equal to 0. And because the first two terms already gave us the desired result, we can conclude indeed that the conditional expectation of it given script fs at time s is indeed I of s. So the second condition for it being a martingale also holds true. So we can conclude that it, the integral, the stochastic integral, is a martingale. We have a remark here. Since it, t greater or equal to 0 is a martingale, where the deltas are the simple processes, of course, then for all t greater or equal to 0, we have that the expected value of it is indeed the expectation of I and 0. And that is an integral from 0 to 0, so that is nothing but 0. So we see that the expected value of it is 0, is equal to 0. And that implies, of course, if we look at the variance of it, the variance being equal to the second moment, the expected value of I square t minus the expected value square, and this second part here, as we see from here, that is equal to 0, that the variance is nothing but the second moment, the expectation of I square of t. Yeah. So we would like to evaluate this right-hand side. We would like to look in detail at this. And that gives us, in fact, a very interesting property. It gives us the so-called Ito isometry. So we have the following theorem to evaluate this. Yeah. The theorem is called Ito isometry for simple processes. And there it's given the following. The expected value of I square at some final time t is in fact the expectation of the integral from 0 to capital T of delta square du. And this is interesting because this integral here is a Riemann integral. Yeah. So delta u is piecewise constant. So the Riemann integral here is in fact a Riemann sum. So it is the sum, I runs from 0 to n minus 1, of delta square ti. So this is the simple function, so the square value times the time interval, delta ti plus 1 minus delta ti. So that is interesting because this is easily manageable, right? The dw term has disappeared, if you wish. Now, if we denote it as the integral from 0 to small t delta u dwu, if we denote our stochastic integral as follows, our Ito integral as follows, then this Ito isometry tells us that in fact this integral square, the expected value of this integral square, delta u dwu square, right? That is in fact the integral of the expected value of the integral of the terms inside the integral square. Delta square, and recall that dw was equal to w in the shorthand notation. So recall the shorthand notation, dwu is equal to dw. So we can take the square inside the integration operator. So we can bring the square inside, and we use the rule dwu is in fact du. Now, how to prove this? Well, again, we do it pretty much the same way as we did before. Yeah, so we have a time interval, we have a time partition. T0 is equal to 0, is less than T1, less than T2, etc., up to Tn, which is the end point of our time interval, capital T. Let this be a partition, T0 till Tn. Let that be a partition associated with a simple process. And the simple process is again delta T, where small t runs from 0 to capital T. Now we have a small t in this interval from 0 to capital T, small t, and let again our index k be such that this t value lies in the interval from tk to tk plus 1. We have an open interval at this side. Now, again, we write out it, and we write it as follows. We first go until time point tk, so it's a sum. I runs from 0 to k minus 1. Delta ti, again, the left point value, times the Brownian increment w ti plus 1 minus wti. And then we have that last term. Again, remember, t is in that interval. So the last term we have is again the left point rule, delta tk times wt minus wtk. And now in order to handle this, we use a short form notation. We will use d sub I for, and it is this term here. It is wti plus 1 minus wti when I is between 0 and k minus 1. Yeah, in this part. And it is defined as wt minus wtk, so it's defined as this part when I is equal to k. Yeah, and in that case, we can take this as one sum, in fact. So a one sum, a sum I runs from 0 to k of delta ti times di. And di has these two definitions. So di is a little different when I is equal to k. And now please notice that wti plus 1 minus wti, in fact, that increment is independent of script fti, yes. And this last part, wt minus wtk, that is independent of ft. Okay, so we can benefit from these properties. All right, let's work it out. Let's continue with our evaluation. And we have to look at I square. Yeah, and I square, I use this notation like in the book, and it is nothing but this, of course, right? IT square. Yeah, it's IT square. And then we have to square, we go back one page, we have to square this. Yeah, we have to square this. And this goes as follows. Of course, this is, first of all, it is the term squared. I runs from 0 to k of delta squared at ti times di squared. But it also has the mixed terms, right? So we have all these terms here. And if we square this sum, we have the mixed terms, 2 times delta ti, delta tj, di, dj. And we can write that as follows, plus 2 times the sum, where I is less than j, and I and j are between 0 and k, times delta ti, delta tj, di, dj. So this combination here, written it up like this is in fact the writing for IT square. Please check it yourself. Now, what we are looking at, what we are looking for is the expected value of IT square. So we look for the expectation of this whole thing. So the expected value of this term here, and the expectation is a linear operator, as you know. So we can take the sum out of this, and we can bring the expectation inside, right? And moreover, it is again, it is a linear operator, so we can bring the expectation inside the first term, and we can add up the sum where also the expectation is inside the second term. So this is just the property of the expectation. Now, if we look at it in detail, we first focus on this second term, because that is relatively easy. Yeah, we focus on the second term, and we have I is less than j. So in this definition, I is less than j. And that means that delta ti times delta tj times di, that is in fact ftj measurable. So this part here, the first 3 terms here, they are in fact ftj measurable. And this last part, dj, which is by definition wtj plus 1 minus wtj, well, you know that that part is independent of ftj. So we split this composition of 4 terms into 2, essentially, in a part which is ftj measurable and a part which is independent of ftj. Well, while doing that, we can easily evaluate this. So notice that delta tj, delta ti, di, and dj are independent random variables, and that gives us that the expected value of this is the expected value of the first one, the 3 terms here, times the expected value of dj, and that is equal to 0, because we know that this expected value is equal to 0. That is a Wiener increment. So that part is equal to 0. Now we focus on the first term. The first term is the expected value of IT square now, and that is equal to the sum, I runs from 0 to k, of the expected value of delta square ti times di square. Now, if we consider this, this part, again, and we look carefully, we have, of course, that delta square ti is fti measurable. Yeah, it is a constant squared. It's ft measurable. It runs up to ti. While di itself is independent of fti. And that remember that di is an increment that is independent of fti, and the same holds true for di squared. So again, we can look at these terms, and we can see that we have a term which is ft measurable and a term which is independent of ft. So in total, the expected value of of delta squared ti times di squared is in fact the sum of the product of the expectations expected value of dti squared times the expected value of di squared. And I runs from 0 to k minus 1. Now note again, if we look at this second term here, the expected value of di squared, that is the expected value of wti plus 1 minus wti squared, when I runs from 0 to k minus 1. And it is nothing but the expectation of wt minus wtk squared when I is equal to k. And we know these expressions. We have seen these expressions before. The expected value of this square difference is ti plus 1 minus ti when we are in this index set, I between 0 and k minus 1, and it is t minus tk when we are at the last index. So we know these expressions and we can use them. So indeed, you see that step by step, we have taken everything inside the expectation. So we indeed can benefit from the fact that we know this expression and that we can replace it by ti plus 1 minus ti. And this expression here, we can replace by t minus tk. So summarizing the second moment, the expected value of I squared is the sum I runs from 0 to k minus 1 of these terms of the expected value of delta square ti times this increment, ti plus 1 minus ti, which we have just seen, plus the last term, the expected value of delta square at tk times this increment t minus tk. And these sums are Riemann sums, expected values, they are constant, basically, the expectations here. So these are Riemann sums. Delta square t is constant on ti to ti plus 1. And therefore we can rewrite this expression as, we can take the expectation out and take the sum in, because the expectation is of course a linear operator. So this is the expected value of the sum I runs from 0 to k minus 1 of delta square ti times this time increment plus the last term delta square at tk times t minus tk. And we can make this finer and finer, the more and more points in the partition with distance, the mesh smaller and smaller. So in fact, we can write this Riemann sum as a Riemann integral. It's an expected value of the sum I runs from 0 to k minus 1 of an integral of such a piece. Remember that this is constant on this. So this is identical. It's the integral from ti to ti plus 1 delta square u du, plus that last one, the integral from tk to t delta square u du. And if we combine this all, we see the Riemann sum as an integral that is nothing but the expected value of the integral from 0 to small t delta square u du, and that is exactly what we were looking for, right? So that expression is indeed the same as this one here. That concludes the proof. And today we conclude with some informal notation. What have we seen? Well, we have seen before already the informal notation dw is equal to dt, right? And that gave us, or that originated from the quadratic variation. The quadratic variation of w in square brackets, wt is equal to t. Now we have looked at this stochastic integral, it, which was the integral from 0 to small t, delta u dwu. That is the integral form for a simple process delta. And we can write this in differential form as follows. dit is then delta t dwt. That is what we can use. And this is handy notation because we can also compute, calculate with this notation, right? Because if we have dit, dit, then we can simply take delta square t dwt dwt. And dwt, recall that is dt. So we can substitute that. So we see that dit is in fact can be written as delta square t dt. And that is the Ito isometry that we are using here. And it is related to quadratic variation again. So we can say the quadratic variation of I, so in square brackets I t, is the integral of from 0 to small t of delta square u du. And this tells us that the Ito integral accumulates quadratic variation of delta square t per unit time. So the quadratic variation of the Ito integral is equal to delta square ti plus 1 minus ti. And in fact, that is similar to the notation for Brownian motion, where the quadratic variation was written like this. W, the in square bracket w, from 0 to t, that was equal to t. And that gave us dwt is equal to dt. So here we see a similarity for the stochastic integral. We have an integral form, we have a differential form, and we can compute with it, we can calculate with it. Well, this concludes the first lecture for today. I thank you for your attention. The claim that in fact the quadratic variation of IT can be written like this, the claim will be in the lecture notes, in the slides. So I will not discuss them in detail, but it will be in the slides. It is a rather simple proof, so therefore you can do it yourself. But my time is up for now, so I thank you for your attention.